Hello and welcome. It is Precalc time with Miss Wesley. We are at the end of our unit on polar coordinates and complex numbers, looking at page 18 of the polar packet, where the heading is roots of complex numbers. That's what we'll talk about today. Before we start, you guys know that my mom hates it when I steal her kitchen utensil, but I'll tell you, that's a risk I'm willing to take. Let's look at this problem here. This almost seems like too easy of a question. How does this have anything to do with finding roots of complex numbers? Let's think back. Now remember, we've been working with complex numbers over the past couple lessons. We know that all complex numbers take the form a plus bi. They encompass all the real numbers and all the imaginary numbers. 7, the number 7, my favorite number, is even a complex number because it could be represented as 7 plus 0i. So the question is, I guess I would call 1 a complex number. It's real. And what are basically the 6th roots of it? What number or numbers could you raise to the 6th power and get 1? Is it a trick question? I know of a couple real numbers that would work. I know 1 has got to be a solution. 1 to the 6th gives me 1. Can you think of another real solution? I mean, that's an even power. So -1 should be another real solution to this equation. So where's the catch? Is there anything else I have to do? Well, absolutely. If you think back to the fundamental theorem of algebra, and I want to jog your memory here, we've been operating based on the fact that every polynomial equation of degree n has n solutions in the complex number system. Every quadratic has 2 solutions. Now, some might be real, some might be imaginary, some might be repeats of others. You have repeated roots where you get the same answer twice, but there are 2 complex solutions. This problem, this equation to solve, should have, count them, 6 solutions that we're going to try and find. And my guess is, my hypothesis is, we got the 2 real answers. I bet you the other 4 are going to be imaginary. Well, let's go to work. I bet we already know enough to be able to find these. Let's use some algebra and move the 1 to the other side of the equation. So x to the 6 minus 1 equals 0 is what we're trying to solve. Does any useful factoring method come to mind? And I'm wondering if you're thinking you could use this as a difference of squares, right? What's the square root of x to the 6? We have x to the 3rd plus 1, the square root of 1, and minus 1, the square root of 1. So plus 1 and minus 1 should be a good first factoring step as a difference of squares. Now, we're not finished there. These are both sums and differences of cubes. So both of these factor further, and we can get our solutions from that factoring. I don't know if you sing a song when you factor this one, but I actually do. I'll set up x to the 3rd plus 1 as sum of cubes using a small little binomial followed by a trinomial. And then warm up the old vocal cords. Goes to twinkle, twinkle, cube root, same sign. So you'll cube root the x. You'll cube root the 1, and then same sign. You'll have an x plus 1 in that binomial. Then take these, and you're going to apply verse 2. Here goes square it, multiply together, and change the sign. So you will square the x, square the 1. In the middle, multiply 1 times x, change the sign to a minus. And you'll see very similar factoring with the difference of cubes. It'll be cube root, same sign with an x minus 1. Square it, x squared and a 1. In the middle, this one will be a plus x instead of a minus x. And here is as far as I can go with our normal classic factoring methods, but it's enough. Notice, I got my first solution, x equals -1. No big surprise, we had predicted that. Do you see another real solution from this one? X equals +1, we were expecting to come up. Now in between, I don't think this is going to factor. I could use quadratic formula. So x equals opposite of b, 1, plus or minus square root of b squared minus 4 times 1 times 1, all over 2a, all over 2. So here are a pair of imaginary solutions to this equation. 1 plus or minus, we'll say I squared of 3 in rectangular form, all over 2. Here are, so far, we've got 4 solutions, 2 imaginaries and 2 reals. The other 2 imaginaries will look pretty similar to the last 2, and they're going to also come from the quadratic formula. So this time, opposite of b, how about a -1, plus or minus, square root of b squared minus 4ac, so just minus 4 over 2. Last 2 answers, -1, plus or minus I squared of 3 over 2. So bravo to us. Did take a little while to get there, but we found, count them, 6 solutions to that 6th degree equation. If you were to take any of these circled answers and raise them to the 6th power, lo and behold, you would actually get the number 1. Today we're going to work in polar form and then maybe convert our final answers to rectangular, and you'll see that as we go. Let's get some ground rules down. It says the complex number, u equals a plus bi, is an nth root of an initial complex number z when z is going to equal this number, right? We could say to the nth power. If z equals u to the nth, u gets to be an nth root. And that's what we're going to find today, a bunch of roots of complex numbers. And we can write this as a plus bi to the nth. Here's an example of it in more of a rectangular form, and when we need polar form, we will definitely be converting. Let's try one initial example before we get a couple more summarization rules at the bottom. Let's find the cube roots of 8i. So in a way, this wasn't an equation that I laid out for you to solve, but we can write our own equation. In a way, let's use the complex number z, and let's figure out z to the 3rd equals 8i. We want to figure out the solution to this equation where when we find z, it's a value that we can cube and then get 8i back. Okay, and we'll use some algebra to get there. So if you wanted to solve this for z, you'd be getting z by itself by cube rooting both sides. And the notation I'll use is going to be a power. I'm going to raise both sides to the 1/3 power, which is the same thing as cube rooting. So 8i to the 1/3 power. The reason I set it up this way is because we just had a lesson on finding powers of complex numbers in polar form, where de Moivre's theorem helped us find those a little bit more quickly. And de Moivre's theorem should apply with any real power, so we can use it a little bit initially here today. On the inside, can you look into the 8i? And can you give me a quick conversion to polar form? Think about 8i. Feel free to use r equals the square root of x squared plus y squared and the definition of tangent. Or, alternatively, because I think this will come out to be quadrantal, think of where 8i falls on the complex plane. 8i is kind of like saying 0 plus 8i. You're going out 0 and you're going up 8. 8 is your y value. So r is going to equal 8 up here. What would theta be? I think we can tell from the picture. Theta is going to equal 90 degrees or pi over 2. Feel free to use the conversions or just try this one visually to get r and theta. And let's rewrite that in this context to the 1/3 power. So this is like us saying take 8 cosine plus I sine, I'll abbreviate that cis, the theta of pi over 2 to the 1/3 power. And if I am kind of just following from the work we did on the previous lesson, de Moivre's theorem would say, okay, not a big deal. Raise the 8 to the 1/3 power. So 8 to the 1/3 gives you cube root of 8, which is going to be 2. And his theorem says, don't raise the pi over 2 to the 1/3 power, multiply the pi over 2 times 1/3, and you get 2 cis pi over 6. And I'm wondering if I'm finished. That's an answer. Everything I did was sound, and it followed the rules that we know about raising complex numbers in polar form to powers, but I don't feel completely comfortable about leaving it like this. Find the cube roots of 8i, solve this 3rd degree equation. I should be expecting, by the fundamental theorem of algebra, 3 solutions. And we'll get a good summary and a strategy for how we get all those solutions down below in a second, but I kind of want to introduce it to you here. You multiplying that 1/3 by pi over 2 leaves open the possibility of a few coterminal angles also working within the context of the problem. Here's what I mean by that. This next step here where I write, okay, so let's take 8 cis pi over 2, raise it to the 1/3. We already went over that I raise 8 to the 1/3, so cube root of 8 is 2 cis. What you're doing, writing it out here, is 1/3 times pi over 2. But what's acceptable is to add 2 pi a couple times and you still get a few more solutions. So I'm going to add 2 pi k, right? Adding or subtracting any whole number, if k is an integer, whole number multiple of 2 pi to pi over 2 shouldn't alter the answer much, right? Because the angle would fall in the same spot. I don't want to go crazy and let k be any number, but to get 3 solutions to this, we actually already found the solution where k equals 0. To get this answer that I circled over here, I didn't add any 2 pi k. I didn't even mention it. So we actually did solve it for k equals 0. We can solve it for k equals 1 and k equals 2, and then we have to stop. You'll see the rule for this below. Like I said, if I go higher, 3, 4, 5, it's going to be redundant. I'm going to be hitting angles that I've already figured out, but plugging in these whole number multiples of 2 pi that we're going to add to pi over 2 will get us a couple more solutions. So what we found here, we can call z sub 0, the first of the 3 cube roots. And I want to see if together in polar form, we can find the other 2. So the second one's going to be 2 cosine plus I sine. And then pi over 6, we can simplify this a little bit. This is 2 cis. Pi over 2 times 1/3, we said is pi over 6, plus 2, I'll say k pi. I'll just reverse the order of that over 3. And then let's plug in k equals 1. It's 2 cis pi over 6 plus 2 pi over 3. Should give us another unique solution. We can simplify that. In polar form, we'll add. It's like adding pi over 6 plus another, this is 2 pi over 3, so plus another 4 pi over 6 to get 5 pi over 6 as an exact value. 2 cis 5 pi over 6 is actually a second solution. You don't believe me? If you cube this, you will get 8i. Mark my words. We'll have plenty of time to practice and check these solutions further on in the lesson. But this actually is trustable as our second answer. And for our third answer, we can plug in 2 for k into one of these expressions here. So we'll say 2 cosine plus I sine pi over 6 plus, now we're plugging in 2 for k, so 2 times 2 is 4 pi over 3. Okay. Add those together, you'll get for a final answer 2 cis, the quadrantal angle, 3 pi over 2. That's going to be your third solution. And I will say again that there's no reason to go in and find, say, a z sub 3 here. If I added another multiple of 2 pi to that angle that we're using here, it'll actually give you a redundant answer that you already have appearing in your list. So there's a need to stay organized about this, and I see a really good summary, a good place you can go back to whenever you're trying to find a root of a complex number at the bottom of page 18. It says when you do have a complex number in polar form, fundamental theorem of algebra says there are exactly n distinct nth roots, and here's how they're given. Z to the 1 over n is going to equal just what we did in the last problem. First step is to take the nth root of the r value from the original complex number. Then it's cis, we'll write it out, cosine plus I sine of what though? Well, it wouldn't just be, De Moivre's theorem would say multiply theta by 1 over n, so take theta over n, and it's not just that, it would be theta plus a few multiples of 2 pi. I'm going to say theta plus 2 pi k over n. You still divide by n, but there's that little added part to it to get more than one solution at times. Same argument here, theta plus 2 pi k over n. To close things off. Now, feel free in your notes to continue using the shorthand format with cis, right? I'll just write this in 2 forms. It would still be the nth root of r, abbreviation for cosine plus I sine, and your angle is going to be theta plus 2 pi k, we'll talk about k in a second, divided by n. So either version of that is going to be okay. Notice what they say are going to be the rules for k. K starts at 0, so for your first answer, you don't have to add any multiple of 2 pi. 1, 2, 3, count up the integers until you get to 1 less than n. So like in this problem above, I was finding a cube root, and I only had to find the z subscripts up to z sub 2. Get ready for the next part of the lesson where we see these rules in action. See you soon.